going to continue from where I stopped last time. I'm gonna read ChatGPT first. Don't really remember. I think that the last time we did this, so this is, I think it is an SR latch, and from the response that ChatGPT gave is probably correct. I thought that this was supposed to set and reset a value based on the enable. So I'm considering the input on top should be the enable, and this one should be the value. So whenever this is on, we're supposed to turn the outputs to whatever the input value is currently at. But based on ChatGPT response, I think that's not exactly what an SR latch is supposed to do. If I do here, okay, so now this time, sometimes I think it doesn't, yeah, so now it doesn't change there. If I let go, then it switches. But I think that based on the schematics, that's what it's supposed to be. And I'm trying to follow this sequence here. I'm just gonna read the GPT response from last time and then continue from this part. The idea obviously is try to build a computer eventually. Not necessarily a computer, but the circuits that I have the most doubt about.
We need to slow this down and separate what is true from what you are inferring, because there is still one conceptual slip. I'll do 3 things, in order. Confirm what is correct about your SR latch. Correct what you are misattributing to N behavior. Define and specify the D latch precisely, with a dot graph, using only your requested labels. No hand waving. 1. Confirmation. Did you build a valid NAND SR latch? Yes. Your circuit is a valid NAND-based SR latch under Turing-Complete's execution model provided. Each NAND's output feeds back into the other NAND through a delay line. The delay lines are only in the feedback paths. The raw output of one NAND is exposed as output. That matches your Verilog in description. So at the electrical, logical level, this component is correct. 2. Critical correction. What you're observing is not enable semantics. This sentence is incorrect, even though it feels true experimentally. It seems to change the output whenever there is a change on the EN, and the output becomes whatever the other input state is. What you are seeing is edge-sensitive resolution of an SR latch, not enable-driven data capture. Here is what is actually happening. NAND SR latch facts, no interpretation. Inputs are active low. The latch reacts when exactly one input goes low. The latch ignores history only during that moment. When both inputs return high, the latch locks. So when you do this, output is off, both inputs on, output stays off. That is hold. Correct. When you do this, change an input to off while the other stays on, output turns on. That is set, because you asserted an active low input. When you then do, turn N back on, output stays on. That is hold, not enable closed. The reason it feels like enable behavior is because you are toggling one input at a time. The other input is static. The SR latch resolves on transitions, not levels. But there is no concept of copying the other input in this circuit. The latch never reads the other input as data. It only reacts to which side was asserted. This distinction matters, because if you carry the wrong mental model forward, the D latch will seem mystical. 3. What an SR latch is versus what a D latch is. Let's lock this in clearly. SR latch. Inputs mean command. Set and reset are actions. No data semantics. No enable. Output is historical. D latch. Input means value. Enable gates when capture happens. Output equals data only during a defined window. A D latch is not a different kind of latch. It is an SR latch with a constrained input generator. 4. D latch construction. Faithful, layered, explicit. We now build a new component that uses your SR latch. Do not modify the SR latch. This layering discipline is essential later. 5. Exact gate level structure of a NAND-based D latch. Inputs. N. Output. Output. Internal gates. NOD, a NOT gate. NANDs. NANDer. SR latch, your existing component. Logical equations, this is the whole point. In a copy codis bar equal to NAND, N, D. Bar equal to NAND, N, not.
So I think that I stopped as I was beginning to do this one. I also realized that I did on the wrong folder there, so I went up some levels. So this one is supposed to be this other one that I just showed there. Telling me to choose one of these. A not. And two NANDs. Looking at this. Just gonna put side by side. There's two inputs. I'll put some music for myself. I'm gonna consider the top one as the enable. Enable is gonna be this one. I think that's basically everything we need to do. Obviously, the problem here is that I'm not really sure if this is correct or not. So I have to think about how I'm gonna verify this. So the obvious way would be to research the truth table, then test here, but it's kind of annoying to do this. It's confusing as well because of the clock here. I think that each tick is like a tick of the clock. So you can only verify the... I have to change the input, then do a tick to see what the output's gonna be. Which is also not very nice. I'm pretty sure that like, it doesn't make sense. There's something that is wrong here. Because if it was right, I think that the behavior should be... Or maybe it is actually. No, it is. This is supposed to be the enable, so whenever this is on, you should set the output to the input here. I'm gonna continue reading there. So if it doesn't work as expected, I'm gonna try to use GPT to explain. Maybe I'm also gonna search there. Latch truth table and schematics as well. The problem is that there's variations of the I think there's the flip flop, the latch, and maybe some other ones. Also, think probably is not a very good idea to do. It's probably better to use the primitive gates, the NAND gates to create the flip flop or the latch, because then it's less abstraction. Like the less. The idea is to be able to visualize everything once I get to the more complex circuits. So probably better idea to use primitive gates. Possible.
Not D. Interpretation. N equal to 0, S equal to R equal to 1, hold. On equal to 1, exactly 1 of S, R asserted, Q, equal to D. No ambiguity. No timing tricks. 6. Dot graph for the D latch, using only your requested labels. Inks copy coded a graph, D latch D,
Put some
D
music
nans,
from us.
N nans, D not, nod, nander, on nander, nans, slash bar, nander, slash or bar, swatch, output. Expanded with explicit intent. Nans generates set, active low. Nander generates reset, active low. SR latch is exactly the component you already built. Output is the SR latch's Q. No other connections. No clocks. No delay lines outside the SR latch. 7. How to verify the D latch, this time correctly. Test only these cases. Case 1, hold. N equal to 0. Toggle D. Output, must not change. Case 2, capture 1. N equal to 1. Equal to 1. Output must become 1. Case 3, capture 0. N equal to 1. Equal to 0.
As just based on the description there is obviously wrong. Yeah.
Output must become 0. Case 4, lock. N, 0. Toggle D. Output must remain unchanged. If this holds, the D latch is correct. If it doesn't, the error is only in the S, R generation, not the SR latch. 8. Why this resolves your confusion about grounding. You were trying to test interface level behavior on a primitive storage element. From here on, follow this rule strictly. Never test a component against behavior it does not claim to provide. SR latch, test set reset hold. D latch, test capture hold. Flip flop, test edge behavior. Each layer earns its semantics. If you want, next we will stack 2 D latches. Add a clock and not. Produce a true master-slave edge-triggered D flip-flop. With a test protocol that cannot lie. But only after you build and validate this D latch exactly as above.
Problem is if I don't put the delay thing here, then I think that is invalid. It doesn't work on the game. I'm not really sure if the game doesn't allow me to build the circuits as it should. And if it doesn't allow me to build, then I have to think about a different way to do this using the circuits that I already have here. I should probably jump into higher levels and just use this 1-bit memory that you get on one of the levels. Probably the best thing to do. And that's the biggest downside of doing this on Turing Complete, because I'm not really sure like about the, it's kind of like a black box. Not sure what's going on here. But I try to, it does work now. I think I was getting a message before about doing this. And here doesn't seem to work. Or maybe when both of them, so I think that this is working actually. So when both are on, it's supposed to be in valid state. But then it's not very clear if I should prevent this or not.
Good. This is exactly the right instinct. Let's ground this operationally, not symbolically. I'll answer in 4 tight sections. What a tick actually means in Turing Complete. How SR latches must be debugged in TC, and how they must not. A concrete, mechanical debug protocol. The most likely concrete mistake in your SR latch. No abstraction gaps. What a tick means in Turing Complete, this matters. A TC tick is not a clock edge. A tick is one global synchronous evaluation step of all components. Important consequences. Combinational logic and memory update together. Delay line advances once per tick. There is no analog propagation time. Feedback without delay, instantaneous oscillation or collapse. Feedback with delay, stateful behavior. So, tick not equal to rising edge. Tick not equal to enable. Tick equal to discrete time system step. This is why latches feel strange if you think in real-time waveforms. 2. How SR latches behave in TC, critical. In real hardware, an SR latch resolves continuously. In TC, it resolves across ticks. This means the first tick after an input change pushes new values into delay lines. The second tick allows feedback to stabilize. The latch cannot update in 0 ticks. So if you do set inputs, observe output immediately. You are observing pre-stabilization state. This alone explains approximately 70% of what you are seeing. Free. Correct debugging protocol for an SR latch in TC. This is the only valid way to debug it. Step 0. Reset mental model. You are not clocking a latch. You are stepping a discrete dynamical system. Step 1. Force a known starting state. Pick a state and force it. Example. Force Q equal to 0. Do this. Set. Input 1 equal to 1. Input 2 equal to 0. Assert reset. Click tick twice. Confirm output equal to 0. Set both inputs back to 1. Tick twice. Now the latch is initialized. Step 2. Test hold. With both inputs equal to 1. Tick repeatedly. Output must never change. If it changes, feedback wiring is wrong. Step 3. Test set. Set. Input 1 equal to 0. Input 2 equal to 1. Tick twice. Output must become 1. Set both inputs back to 1. Tick twice. Output must stay 1. Step 4. Test reset. Same procedure, mirrored. Important rule. Never evaluate after 1 tick only. SR latch stabilization in TC requires 2 ticks minimum because tick 1, feedback enters delay line. Tick 2, feedback re-enters NANDs. If you only tick once, you are literally sampling the circuit mid-resolution. 4. The most likely actual wiring error, concrete. Based on your Verilog, here is the likely issue. You expose the raw NAND output as output, but are testing behavior that requires the post-feedback stabilized value. In TC, the stable latch state exists after the delay line, not before it. Correct rule. Delay lines belong only in feedback paths. Output must be taken from a NAND output. But you must wait 2 ticks after any input change. If you instead, accidentally, took output from the delay line, or mixed delayed and non-delayed paths asymmetrically, or changed inputs and sampled immediately, the latch will look broken while being structurally correct. 5. Minimal checklist, use this literally. For the SR latch. 2 NAND gates. Each NAND output feeds the other NAND through a delay line. No delay on external inputs. Output, taken from one NAND output. 2 ticks per test step. Inputs interpreted as active low. If all 6 are true, the latch works. 6. Why this feels harder than real schematics. Real schematics assume analog time, continuous propagation, metastability resolution. TC replaces that with discrete time, explicit delays, synchronous evaluation. So you must replace waveform thinking with state transition thinking. You are effectively doing model checking, not probing a circuit. 7. What to do right now. Before touching the D latch. Retest your SR latch using the 2-tick rule. Write down observed transitions per tick. Confirm it matches the SR latch truth table. Only once this is solid should you wrap it into a D latch. If you want, next message you can paste one tick-by-tick trace, and I'll tell you exactly whether the wiring or the testing is wrong. No guessing.
Inputs. Okay, so far, seems like it is supposed to act in the way that it's saying here. Yeah, but that's the problem, because when I change here, it changes there automatically, so not really sure what is the relationship with the clock here. But I think it is doing what it's saying that it should do. So I exported the circuit to Verilog without the delay lines, because I was gonna share with ChatGPT. I'm gonna delete the ones that I have here, then export again. Then copy and paste to share with ChatGPT and ask if that's the correct one. Then after that, I have to use this one to build the latch again. To try to build the latch.
Now we can be precise and close the loop. I'll do 3 things. Formally confirm whether your SR latch is correct. Explain exactly why it is correct in TC terms. State unambiguously what the next circuit must be, and why, D latch, not DFF yet. No speculation. 1. Is your SR latch correct? Yes. What you have built is a correct NAND-based SR latch under Turing-Complete's discrete time semantics. Let's rest that conclusion on structure, not behavior anecdotes. Structural properties of your circuit. From your Verilog. 2 NAND gates, NAND 0, NAND 1. Cross-coupled feedback. Each feedback path passes through exactly one delay line. No delay on external inputs. Output taken directly from a NAND output, wire 4. This is exactly the canonical transformation required to make an SR latch well-defined in a synchronous tick-based simulator. There is nothing missing and nothing extra. 2. Why this circuit is the correct SR latch in Turing Complete. This matters, because TC is not analog hardware. In real hardware, cross-coupled NAND stabilize via analog propagation delay. In Turing Complete, all logic updates simultaneously per tick. Therefore, feedback must be delayed explicitly. One delay element per loop is both necessary to prevent instantaneous recursion, sufficient to preserve bistability. Your design satisfies the invariant. Every directed cycle contains exactly one state-holding element, delay line. That invariant is the discrete time analog of propagation delay exists. So yes, this is the faithful SR latch, not a hack. 3. Why your SR latch must not be improved further. Important discipline point. An SR latch is not usable directly. It is a primitive. It has an awkward, unsafe interface by design. That awkwardness is the reason higher-level latches exist. You should freeze this component now and never touch it again. Name it something explicit, for example. Nginx copy, codes. This will save you later confusion. 4. What circuit comes next, and why? The next circuit is level-sensitive D-latch. Not the flip-flop yet. Why? Because the dependency chain is rigid. CPP copy code is their latch, D-latch. You cannot skip the D-latch without hiding control semantics, breaking the correspondence with real schematics, losing the ability to reason about transparency versus opacity. Your own stated goal, faithful to real systems, no shortcuts, forces this order. 5. What the D-latch contributes conceptually. This is the key abstraction shift. SR latch stores state. D-latch introduces controlled observation of data. In other words, SR latch answers, what should the state become? D-latch answers, when is data allowed to influence state? This when axis is the beginning of time as a design parameter, which is why it belongs in phase 0. 6. What the D-latch will look like, preview, not schematic yet. The D-latch contains your SR latch. Derives S and R from N. G. Uses 2 NAND gates. 1 NOT gate. No clocks. No delay lines outside the SR latch. Its invariant will be when n equal to 0, state is invariant. When n equal to 1, output equal to D after stabilization. That is the bridge between state exists and state is controlled. 7. Correction to your checklist, important. Right now your phase 0 marks are slightly inconsistent with reality. You should adjust them to reflect what you have actually built. Scopy code phase 0, time, state and causality. VSR latch, NAND, active low delayed feedback. Level sensitive D latch. Edge triggered flip-flop master slave. Clocked invariant probes and cycle counter. This matters because the D latch is not optional glue, it is the semantic hinge. 8. What we do next, concretely. Next step, single, focused. Build a D latch component that wraps your SR latch. When you're ready, say so, and I will give you exact gate list, exact wiring,
open the path.
dot graph, exact TC debugging protocol, tick by tick. No ambiguity, no symbols beyond what you already used. You are now on solid ground.
They are exporting to a predefined path there, and I'm putting the path to the project. So every time I have to select that path, I think we're just gonna open the path that they have there. For the exports. Because obviously, instead of writing down to ChatGPT each time what the circuit looks like, is it much easier to just export the Verilog and then check. This one.
Yes. This is a correct level-sensitive D latch, both structurally and semantically, given the conventions we established. I'll be precise, and then give you a deterministic verification protocol that removes guesswork, plus how to instrument it so you're not just toggling switches blindly. Structural verification, no behavior yet. Let's restate what your D latch actually is, mechanically. Ports, by your intent. Input 1, N. Input 2, D. Output, Q. Internal logic. From your Verilog. Verilog copy code wire 0 equal to input tone, N. Wire 1 equal to input 2, D. Wire 5 equal to not D. Wire 3 equal to NAND, N, not D, S. SRLatch NAND, input 1 equal to wire 3, input 2. That corresponds exactly to. Mathematica copy codes equal to NAND, End. R equal to NAND, N, D. Feeding an active low NAND SR latch. This is the canonical NAND-based D latch. There is no wiring error here. 2. Behavioral contract of this D latch, what it must do. This latch has level-sensitive semantics. Important. Q, D, does not mean instantaneous. In TC it means after stabilization across ticks. 3. Correct test protocol in Turing complete, non-negotiable. This is the only reliable way to verify it. Rule 0. Always wait for stabilization. Because. SR latch contains delay lines. D latch wraps SR latch. Resolution requires 2 ticks minimum. Assume 2 ticks per state change. Test a, hold behavior. Initialize latch. N equal to 1. Equal to 0. Tick x2, output must be 0. Disable latch. N equal to 0. Tick x2. Change D. Equal to 1. Tick xn, any number. Expected. Output remains 0. If output changes here, D latch is wrong. Test B, capture 1. N equal to 0, D equal to 0, output known equal to 0. Set. Equal to 1. N equal to 1. Tick x2. Expected. Output equal to 1. Set on equal to 0. Tick x2. Toggle D arbitrarily. Expected. Output remains 1. Test C, capture 0. Same as above, mirrored. One line invariant, use this mentally.
This one is wrong. Hold on, maybe I just did one there. Oh, I did two. Yeah, so I'm not sure if there's something wrong. It says that it's correct based on the Verilog, but it looks like based on the task it's not working. I will run the other task, then I'm gonna probably run it again, and then ask ChatGPT about it to see what it thinks. Because based on the Verilog, it says that it's correct, but based on the task, it's not correct. Yeah, so this, but it is just 2 ticks. Maybe this one is correct, but it turns off. Yeah, so I'm gonna finish reading, then I'm gonna ask about this.
Mentally. Output may change only on transitions where N equal to 1. Output must equal D after stabilization. Output must be invariant when N equal to 0. Your circuit satisfies this. 4. Why your intuition still feels shaky and why that's normal. 2 reasons. 1. TC ticks are not clock edges. You are not opening and closing a latch in time. You are stepping a discrete dynamical system. So instead of When n goes high, value passes through. You must think. When n equal tune, the next fixed point of the system encodes D. This is subtle but fundamental. 2. SR latch resolution is indirect. You never see Q equal to D directly. You see, NANDs assert S or R. SR latch resolves. Feedback stabilizes. Output emerges. So without instrumentation, it feels opaque. 5. How to debug faster, this is important. You're right, toggling inputs manually is not scalable. Use wire probes strategically. Place probes on N, D, S, wire 3. Wire quattro. Q, output. Now you can observe. Whether S, R are ever both 0, they must not be. Whether hold condition produces S equal to R equal to 1. Whether capture produces exactly 1 low. This turns debugging into logic inspection, not guessing. Optional, build a micro test harness, worth it. Inside a sandbox, not component factory. Use a counter, a ROM or switch sequence. Your D latch. Drive N through a known sequence. Observe Q across ticks. This is how real hardware is validated. 6. Answering your what's next question precisely. Now that SR latch is correct. D latch is correct. The only correct next step is edge triggered D flip-flop, master slave. Why? Because arithmetic, phase 1, assumes edge-based state. Registers require atomic updates. Pipelines are meaningless with level-sensitive storage. A flip-flop is 2 of your D latches plus inverted clock. You are now perfectly positioned to build it faithfully. 7. Update your phase 0 checklist, accurate. Nothing skipped. Nothing faked. If you want, next message I will specify the exact master-slave wiring. Explain why the clock must be inverted. Give you the verification protocol that proves edge-triggered behavior unambiguously. You're doing this the right way.
You can rotate the gate by pressing space. Maybe if I switch the inputs, let's see. The only difference would be the knots would go here. This one goes here. You know, so disable. Yeah, I think now is working. So probably the issue is that the inputs were inverted the way that I was testing there. Yeah. Oh no, because now if I turn on here, it's supposed to stay off, but it's turning on again. Oh, maybe because it did say that it's not instantaneous. So maybe it is working. Maybe that's how it's supposed to be done. And so I think this way is correct. So it said that it's correct because it was looking at the Verilog, but I thought that was incorrect because I was switching the inputs. I think that's how it's supposed to work. I'm still gonna read the response before moving on to the flip-flop. Let's see what it says.
Good. This is exactly the point where TC's execution model collides with textbook expectations. Nothing is wrong with your reasoning. The missing piece is initial conditions, plus active low polarity, plus which side you exposed as output. I'll walk this mechanically. No hand waving. First, your observation is real, not user error. This symptom is key. Initial conditions, with no ticks yet, the output looks on. That already tells us something decisive. Your latch powers up in an arbitrary state. Specifically, Q equal to 1. That is expected for an SR latch, unless you explicitly initialize it. Real hardware does the same, unless reset circuitry exists. So the test you ran is not actually test A yet. You never initialized the state. 2. Why your test A cannot work without initialization. You implicitly assumed N equal to 0, D equal to 0 output should be 0. That assumption is false. For a D latch, hold means preserve whatever state already exists. Since your latch started at 1, N equal to 0 will preserve 1 forever, exactly as you observed. So this behavior, N equal to 0, toggle D, output remains 1, is correct, not a bug. 3. The real bug, you never forced a known state. In TC, SR latches do not self-initialize. Therefore, every test must begin by explicitly setting Q. This is non-optional. 4. How to properly initialize, this fixes your confusion. To test a D latch, you must first force Q equal to 0, or Q equal to 1. Here is the correct procedure. Step 0. Force Q equal to 0, explicitly. Set N equal to 1. D equal to 0. Tick twice. Observe output, it must now be 0. Set on equal to 0. Tick twice. Now the latch is in a known state. If this step fails, then there is a wiring error. If it succeeds, everything downstream works. 5. Rerun test correctly after initialization. Test A, hold. Start from Q equal to 0, initialized as above. N equal to 0. Toggle D between 0 and 1. Tick arbitrarily many times. Expected, output remains 0. This will now pass. 6. Why your initial test looked like D latch is broken? Because the following chain happened. SR latch powered up as Q equal to 1. N equal to 0, hold. You toggled D, ignored, correct. Output stayed 1, looked wrong but wasn't. You were unknowingly testing memory retention, not data capture. 7. One more subtle point, important. Look at your wiring. Mathematica copy codes equal to NAND end. R equal to NAND, N, D. When N equal to 1, D equal to 0. You get equal to NAND, 1, 1, equal to 0, set. R equal to NAND, 1, 0, equal to 1. So D equal to 0 sets Q equal to 1 in your polarity. This means your latch is logically inverted with respect to Q equal to D. That is not an error, it is a polarity choice. You expose the set dominant NAND output as output. So your latch actually implements in a copy code output equal to, when in equal to 1. This explains everything you are seeing. 8. Why this happened, and why it's normal. NAND-based SR latches come in two polarities. Q true. Q bar true. You exposed Q, not Q. Textbook diagrams often hide this by naming outputs ambiguously. TC does not. Two valid fixes, choose one, both are real hardware. Option A, accept inverted polarity, simplest. Document. In a copy code output equal to not D, when in equal to 1. Use it consistently. Many real designs do exactly this. Option B, add a not at the output. Expose true Q. This is what most D-latch symbols imply. 10. How to verify capture correctly now. After initialization. Capture test. Force Q equal to 0. Set. N equal to 1. D equal to 1. Tick X2. Expected. Using current polarity, output equal to 0. If inverted at output, output equal to 1. Both are correct, depending on polarity choice. 11. Final verdict. Your SR latch is correct. Your D-latch logic is correct. Your test failed because you did not initialize state. Your output polarity is inverted relative to expectation. This is not a mistake, it is an exposed truth about real hardware. 12. What comes next? No ambiguity. Before moving to the flip-flop, you must decide. Do I want output equal to Q or output equal to Q? Once decided, lock it in. Then, build master-slave D flip-flop. Using 2 copies of this D latch. Plus clock inversion. If you want, next reply I will. Normalize the polarity cleanly. Then give you the exact master-slave wiring. And a test that proves edge-triggered behavior beyond doubt. You're not stuck, you just hit the first real hardware truth.
Kind of hard to think about what this means philosophically or physically. Or why does this work and how does it fit into the bigger context? I think that once I'm gonna try to build fast and not stop too much on this smaller gates, then once I get to a point where I have a bunch of gates connected, like on higher level abstractions, then I can spend a bunch more time trying to clarify even more how everything is connected. Because then I'm gonna be able to know, to see where this is connected on the bigger circuit, to think about in physical terms and fundamental principles what it means exactly to have this structure on the logic circuit.
Mistake that causes 90% of latch confusion. With that fixed, your D latch. Good. That correction, which signal fans out to both NANDs versus through NOT, is exactly the polarity mistake that causes 90% of latch confusion. With that fixed, your D latch is now conceptually and structurally correct. Now we move forward, and the ordering matters. What is the next step? Yes, edge-triggered D flip-flop, master-slave. Not because it's next on the list, but because nothing above this level should be built on level-sensitive storage. If you skip this and move to arithmetic or registers, you will accidentally build transparent pipelines, smear state across ticks, lose the ability to reason about one update per cycle. So, D flip-flop is the first clock state abstraction. Everything else depends on it. What an edge-triggered D flip-flop really is, no mysticism. A master-slave DFF is 2D latches, driven by opposite clock phases, with no combinational path from input to output in a single phase. That's it. There is no new logic concept introduced here, only temporal separation. Canonical structure, exact, gate faithful. Components you already have. Latch, level sensitive, ND. Signals. CLK. D. Q. Wiring. Master latch samples when CLK equal to 1. Slave latch samples when CLK equal to 0. Dot graph of the master slave.
remember correctly, the clock goes in the middle, connects both of them. Here like this. Okay, so there.
The master slave D flip-flop. Ruscopy codedigraph. DFF master slave. Latch master. CLK. Latch master N. CLK. Not CLK. Not CLK. Latch slave N. Latch master, output. Latch slave D. Latch slave, output, output. That is the entire circuit. No delay lines outside the latches. No extra NANDs. No clock gating. How to understand its behavior in TC terms? Think in ticks, not edges. Assume stabilization takes 2 ticks per latch, as before. When CLK equal to 1. Master latch is transparent. Slave latch is holding. D can change. Internal master state updates. Output cannot change. When CLK transitions to 0. Master latch closes. Slave latch opens. Slave captures master's last value. Output updates exactly once. This is why it is edge triggered. There's only one tick window where new information can cross both latches. How to verify the D flip-flop? This is decisive. Initialization. Set CLK equal to 1, D equal to 0. Tick X2. Set CLK equal to 0. Tick X2. Output now known equal to 0. Edge test. Hold CLK equal to 1. Toggle D arbitrarily. Tick many times. Output must not change. Set CLK equal to 0. Tick X2. Output updates once. Toggle D again with CLK equal to 0. Output must remain stable. If this holds, you have a real flip-flop. Why this completes phase 0? At this point you have a primitive storage element, SR latch. A controlled transparent element, D latch. A discrete time state element, D flip-flop. This resolves time versus state. Transparency versus opacity. Level versus edge semantics. From here on, time is explicit and tractable. What should be built after the D flip-flop? Important. Before arithmetic, you should build instrumentation, not data path. Next 2 things, in this order. 1. Clocked invariant probe. A tiny component. Input, signal. Input, clock. Output, change this cycle? This teaches you what state change really means. How to detect hazards later. 2. N-bit, register with write enable. Built from ND flip-flops. Shared clock. Per register enable. This becomes the atom of all CPUs. Only after this should you go to phase 1, adders. Updated mental model, lock this in. SR latch, state exists. D latch, state may observe data. D flip-flop, state updates exactly once per cycle. Register, named, architectural state. You are now past the hard conceptual wall. Everything after this is composition. If you want, next step I can sanity check your DFF once you build it, or help you design the invariant probe. This pays off massively later.
There's only one. Let's both go here. And from what I remember, that's how it's supposed to work. The master slave. I do think that the circuit is correct here. I don't remember the clock very well. But the biggest uncertainty I have is over the clock on how it works on Turing complete. That's the problem here. And I'm not really sure. Like, it looks like it's just flip-flopping the regardless of what I do there. So it doesn't look like it is correct. When I export this, then ask.
Good catch. What you are running into now is not a logic error in the master-slave structure. It's a tool semantics mismatch. You are trying to use TC's autonomous clock source as if it were a controllable clock signal. It isn't. Let's disentangle this carefully. What the TC clock actually is and is not. T-clock is not a clock input you can hold high or low. It is an oscillator with period equal to 2 ticks that toggles automatically on every tick, starting in an implementation-defined phase, often high. So these things are true. You cannot set CLK equal to 1 and hold it. You cannot single-step edges. You cannot control duty cycle. You cannot pause the clock. Therefore, using TC clock directly while debugging sequential logic will make everything look like it's toggling randomly, even if the circuit is correct. This is expected. 2. Why your flip-flop appears to toggle regardless of input. Look at what you built. Master latch n equal to wire 1, clock. Slave latch n equal to not, wire 1. That is correct, master-slave wiring. But since wire 1 toggles every tick, the system is doing this. Objective ECOP, code at tick 0, CLK equal to 1, master transparent. Tick 1, CLK. So the flip-flop is working, but you are feeding it a clock you cannot control, and observing it mid-flight. In other words, you built a correct synchronous element, then attached it to a free-running oscillator, and tried to reason about it interactively. That cannot work. 3. Key rule, lock this in. Never debug storage elements using TC clock directly. This is not advice. It is a constraint imposed by the simulator. 4. What you must use instead, this resolves everything. For debugging and validation, you must use a manual clock signal, not T-clock. That means a normal 1-bit input, or a button, or a controlled toggle built from logic. Treat clock as just another input wire during testing. Later, once the system is verified, you can drive it from a real clock. 5. How to debug your D flip-flop correctly. Step 1. Replace T-clock. Remove this. Ngens copy, code at clock, wire 1. Replace it with PGSQL copy, code input clock, manual 1-bit input, wire 1. Keep the NOT gate. Now you have full control of CLK. Ability to hold it high or low. Ability to create edges when you want. This mirrors how real flip-flops are verified in simulation. Step 2. Correct test procedure, manual clock. Assume CLK is a manual input. Stabilization requires 2 ticks per latch. Initialization. Set CLK equal to 1. Set input equal to 0. Tick x2. Set CLK equal to 0. Tick x2. Output is now known, 0. Edge test. Hold CLK equal to 1. Toggle input arbitrarily. Tick many times. Output must not change.
Not sure about this because it was toggling there. Maybe it takes one change of state to work. Not really sure.
Change. Toggle KLK from 1, 0. Tick x2. Output updates once. Hold CLK equal to 0. Toggle input. Output must remain stable. If this holds, the flip-flop is correct. 6. Is your master-slave wiring correct? From your Verilog. Master latch. N equal to wire 1. D equal to input. Slave latch. N equal to not, wire 1. Equal to master output. That is exactly the canonical master-slave DFF. There is no structural error here. The problem was using an uncontrollable oscillator as a control signal. 7. Why counters are also the wrong tool for now. You mentioned possibly using an 8-bit counter. That won't help yet, because counters are already clocked state. You'd be stacking unknown state on unknown state. Debugging becomes strictly harder. First, validate the flip-flop with a manual clock. Then you can derive clocks from counters later. 8. The correct mental separation, important. There are two distinct roles. Clock is a control signal. Must be manually controllable. Used to verify correctness. Clock is a time base. Free running. Used only after correctness is established. You are currently mixing these roles. 9. What this unlocks next. Once the D flip-flop is validated with a manual clock, you can safely mark edge-triggered flip-flop equal to complete. You can then build sen bit registers, write enable logic, cycle counters, real clock trees. At that point, using TC clock makes sense. 10. Bottom line. Your D flip-flop circuit is structurally correct. Your observations are explained entirely by TC clock behavior. The fix is to replace TC clock with a manual clock input for testing. After validation, reintroduce TC clock at the system level. Once you do this, the behavior will suddenly snap into focus. If you want, next we can build a proper clock divider, gated clock from your flip-flop, or move on to registers and invariant probes now that phase 0 is truly complete. Good. The flip-flop you just showed is structurally correct, and, more importantly, you now validated it under a controllable clock, which means phase 0 finally has a solid semantic footing. From here, the question is not what's next in a linear sense, but what dependency graph actually gets you to UO, speculation, and real data paths, without lying to yourself along the way. I'll answer in 3 layers. Confirm where you are. Explain why not to jump to ALU yet. Give a concrete next build sequence that preserves causal clarity and directly feeds into UO later. Where you actually are now. You have completed. Explicit time, tick-based. Level-sensitive storage. Edge-triggered storage. Manual clock discipline. What you do not yet have, despite appearances. A notion of architectural state. A notion of write enable. A notion of who owns state when. Those are not memory topics in the abstract. They are the core problem of UO and speculation. Arithmetic is trivial compared to that. So phase 0 is almost done, but there is one missing piece that your own ledger already hints at. Clocked invariant probes and cycle counter. That item is not bookkeeping. It is the first control structure. 2. Why moving to ALU logic now is a trap. You already know how adders work at the gate level. Building them now gives you 0 new conceptual leverage for hazards, speculation, reordering, rollback, control flow. Out-of-order execution is not hard because of arithmetic. It is hard because of state ownership across time. If you build ALUS before you build state aggregation and control, you will later retrofit control onto data paths that were not designed to be stalled, replayed, or squashed. That's exactly how real designs accumulate accidental complexity. So do not jump to phase 1 yet, even though it looks tempting. Third, the correct next step, and why. Immediate next build, single-bit register with enable. This is not redundant with your DFF. Conceptually. A DFF answers, what was D at the edge? A register answers, should I accept a new value at this edge? That conditional is the first appearance of control versus data separation. Mechanically, this forces you to introduce a write enable, a mux in front of storage, a stable hold path. This is the minimal unit of architectural state. You should treat this as the real completion of phase 0. 4. What this unlocks immediately. Once you have a register with enable, you can build a cycle counter, state plus enable. Invariant probes, this must never change unless explicit stalls, enable equal to 0. Bubbles, enable equal to 0 plus injected value. Those are the same mechanisms used later for pipeline stalls, scoreboard holds, rob commit gating, speculative suppression. This is not a detour, it's the spine. 5th, revised execution order, minimal rewrite. You don't need to rewrite your whole ledger, but you should pull one item forward and insert one missing abstraction. Revised phase 0, tightened. V, explicit 2-phase clock discipline. Level sensitive latch. V, edge triggered flip-flop. Register with write enable. Clocked invariant probes and cycle counter. Only after that do you move on. 6. Then what, and why this ordering matters. After register with enable, the natural progression is phase 1, only the minimum arithmetic. Not the whole ALU zoo. Just enough to feed control experiments. Half adder. Full adder. Ripple carry adder. Stop there. Why? Because carry look ahead matters only when timing matters. Timing matters only once pipelines exist. Pipelines require registers with enable and stall semantics. You see the dependency loop. 7. The real conceptual jump you are approaching. The moment you build a register file with enables and multiple read ports, you will automatically run into raw hazards. Read before write ambiguity. Bypass versus stall decisions. At that point, out-of-order execution stops being abstract. Reservation stations and ROBs become obvious generalizations of who is allowed to write this register now. That's why this path works. 8. Summary, no fluff. Your DFF is correct. You fixed the right problem, clock semantics. Do not jump to ALU breadth yet. Next build, register with enable. Then, invariant probes and cycle counter. Only then, minimal arithmetic. This path minimizes rewrites and maximizes insight into UO and speculation. If you want, next step we can design the register with enable formally, state equation plus invariance, or sketch how that exact structure generalizes into a ROB later. But mechanically, the next circuit to build is unambiguous. Good instinct. You are exactly at the point where data selection and state admission become inseparable, so the order matters, but only one way. Short answer first, then the circuit. First, order, mux first, then register with enable, not simultaneously. A register with enable is definitionally a storage element whose next state is selected between the old state, a new data value, based on an enable signal. That selection is a mux. If you don't explicitly build and understand the mux as a combinational selector, you will accidentally smuggle control into storage again. So the correct sequence is: build a 2-1 mux from gates. Feed that mux into a D flip-flop. The enable drives the mux select. This preserves abstraction boundaries. Combinational selection first. State update second. Anything else collapses causality. 2. What a register with enable is: state equation. Let Q equal to current stored value. D equal to external data input. N equal to write enable. Q next equal to value after clock edge. Then the invariant is in a copy code Q next equal to EN D Q. That equation is the design. Everything else is implementation detail. 3. Build the mux from first principles. 2-1 mux truth. Inputs: A equal to old value feedback equal to new data. Cell equal to enable. Output: in a copy code out equal to cell A SELB. Gate level structure. Required primitives: and or NAND plus not. Or non-composition. You can implement or via De Morgan if you want to stay NAND pure, but conceptually this is the shape. 4. Graph 2 1 mux. Here is the explicit structure, no shorthand. Rust copy coded to graph. Mux 2 1. Ranked or equal taller. A label equal to A old value. Label equal to B new data. Cell label equal to cell enable. Not 1 label equal to not. And 1 label equal to and. And 2 label equal to and. Or 1 label equal to or A and done. Cell naton. Not 1 and 1. B and 2. Cell and 2. And 1 or 1. And 2 or 1. Or 1 out label equal to mux out. This mux is purely combinational. No delay lines. No storage. No clock. That's important. 5. Now, register with enable equal to mux plus DFF. Once the mux exists as a component, the register is trivial. Structure: feed Q back into mux input A. Feed external D into mux input B. On selects. Mux output goes into DFF. DFF output is Q. Graph. Register with enable. Rust copy coded to graph, reg with enable. Ranked are equal taller. Label equal to D, data in. N label equal to N, write enable. Label equal to Q. This diagram is the canonical register used everywhere. Pipeline latches. Architectural registers. ROB entries. Scoreboard bits. Valid flags. Ready bits. You are not building a toy here. 6. Why this matters later. Ooh, preview, no hand waving. Later, when you build a ROB entry. A reservation station slot. A pipeline register. You will reuse this exact structure, just widened and replicated. Out of order execution is not fancy scheduling logic. It is hundreds of registers with enables driven by different conditions. If this primitive is clean, everything above it is clean. 7. What to do next, concretely. Build the mux as its own component. Verify it exhaustively, 4 input combinations. Then wire it into your existing D flip-flop. Expose A. D. N. Add probes on. Mux output. DFF output. Once that works, your phase 0 is actually complete. Next after that. Cycle counter equal to register with enable plus adder. Stall logic equal to enable suppression. Bubble injection equal to forced mux select. All the hard stuff starts there. When you're ready, we can formalize invariants for the register, what must never change unless n equal tune.
I'm not sure what old value is supposed to be here. Should be. Should I put 3 inputs? I don't think that makes sense. So, but I'm pretty sure I can't do this on Turing complete. Yeah. I think I'm gonna stop here streaming. I'm gonna spend some time off stream talking to ChatGPT to see if I understand what it means by this A off. But probably I'm not gonna do anything else off stream. Next time I'm going to continue from this point here. Just try to build this register with enable. The main short-term goal that I have is to create a full data path, like one of these here. I want to build on Turing Complete so I can have hands-on practice to see. And the biggest challenge that I'm thinking about, that I'm not really sure if I'm going to be able to do it or not on Turing Complete, is to verify the inputs. But I think that they have some gates there that I can use. But the thing is, I'm not really sure, obviously, because I never did anything here like this. But I'm hoping that I can use some of these gates here. Maybe it's only on the sandbox that I can use. I'm pretty sure that there is one on the sandbox that is a program and another one that is a terminal or something like this. So maybe I can, or there's also one that is a hex, I think. So maybe I can I can create something like this where I have the input and output, and I can visualize the calculations in order to verify if it is correct or not. And the main thing that I'm trying to, there's several different things that I'm trying to clarify, but the main one, the first one, would be the control logic around the speculative execution and the out of order execution as well to prevent data hazards. Data hazards are what happens when you try to execute instructions out of order and you end up writing before reading, for example, on the data, so you get the incorrect output. That's basically what I'm trying to clarify, because here obviously you can see on the conceptual level what is happening, but the nuances is the problem, because like all of this stuff here is basically a black box of what's actually happening on the control logic to allow all this stuff here to happen. So that's basically what I'm trying to clarify. And I'm not really sure if I'm gonna be able to do it or not because of Turing Complete. I'm thinking that if I can't do it, I'm probably going to switch to Verilog. So what I can do is just obviously export all the gates that I have there, and then I can start either another project or on the same folder. I can go over with ChatGPT. There are other software you can use as well to verify Verilog outputs, and then obviously it's more professional because Verilog is the language that they actually use to create hardware circuit simulations to send to the pipeline to produce the actual hardware on the machine. Maybe switching to Verilog at some point is probably the best thing to do. The other part that I'm not really sure is whether or not I should recreate like all of the components, because some of them you create through the levels there, through the campaign. And that's how you unlock them on the thing there, the sides, the built-in gates. So for example, program counter, I'm not really sure if I should use the 64-bit counter that they give there. Probably I'm gonna do that instead of recreating, because it's not very interesting. And there is a level here where they show how to do this, I think. Though I think this is one of the levels before there. 5. Yeah, counter here. So this is the counter. And obviously it's built with the other components that you build on the other levels. I do remember spending some time trying to understand this. But it's basically splitting decoding the byte that it receives here. And this is kind of the downside because like I'm forced to use string complete. Like they're it's kind of like using a compiler where if you program on a higher level language, you can't. Like there are decisions that the compiler builders, or the compiler developers made that you can't do from the higher level language because it's obviously a trade-off. So here's like basically the same thing. I can't really decide at what level I can see the abstraction. So here obviously is already 8 bytes that is passing through the wire, but on a real case would be more like it would be more wires to produce the 8 bytes. So it's obviously a trade-off that like the person that created the game has to decide. It's kind of like, but it's not that big of a deal, I think. But I think for more granularity, it's probably better to do it on Verilog at some point, I think. But yeah, obviously receives 8 bytes, 8 bits here, 1 byte, and then it decodes and then uses AND and XOR on a cascade to do the sum of the value, I think, based on the clock. I think is this input here, maybe. Maybe this is 1, I don't know. So this on the clock would go up to the amount of instructions that the CPU has, and then at each point you would go through the whole circuit here at each clock, I think. So fetch, you decode. I think this is fetch and decode this unit here from the instructional memory. And the instructional memory is just a bunch of it's like a row of zeros and ones that based on the control logic, the wires, depending on the control logic of the wires, is gonna understand what is the instruction. It's basically the job of this part here. So there's gonna be some bits on the row that determine what the instruction is based on the control logic, and the other ones are gonna be the data of the instruction. Yeah, so I'm gonna stop here. Next time I'm just gonna continue from where I stopped today. So see you next time.